Thanks for having me here. Since the workshop is about data simulation uncertainties, I try to tackle this model discrepancies issues using data simulations. So the general idea is we often use data simulation to improve our initial conditions. But here in my talk, I want to use data simulation in future times to improve the forecast. So here's the outline of my talk. So I'm going to talk about the multi-model ensemble schemes and motivations, why we need to do the cross-pollination, and the methodology, and I will demonstrate in the Langue 96 experiments. So for the multi-model ensemble schemes, we all know that we used to working on initial condition ensembles, try to account uncertainty in the observations. Then we realized we have model discrepancies, structure model errors, so we developed multi-model ensembles. And we have been seeing a lot of multi-model ensembles before, has been already developed, like the ensembles, the North American multi-model ensembles, the CM5, right? There has been some results suggesting the multi-model ensemble forecast outperform the single model forecast, right? Well, actually, so there are some papers we invested. Right. Okay, can you see those? We found that this may not be always the case. Anyway, so for the motivations, so what do we usually do when we have a multi-model ensembles? We try to do some kind of statistical approach, and to combine the ensembles of each individual models, then to produce a forecast PDF. Right. For example, so if we think about a Langue 63 example, so let's say we have just model A and model B. Each of them we have like 3-member ensemble forecast. Right. This is a X variable, Y variable, and Z variables for each of the figures here. Right. So I understand that this is a very poor interpretation of the models living in the high-dimensional space. Right. So normally we do is instead of combining them dynamically, we usually just looking at the end of the lead time of the interest, and we do some kind of statistical processing, and we generate a PDF at that time. Right. The problem with this is there's no kind of a communication between the models when they're making the forecast during the future. Right? So if we could let them communicate during the time they're making forecasts, we actually can kind of explore their dynamic information interactively. So here, that's the motivative, right? So statistical processing cannot explore the richness of the multi-model dynamics. So our aim is basically we want to create a communications between those models. So between the launch time and the target lead time. Okay, so we published a paper called the Multi-Model Cross-Pollination Time in 2017. So here we just want to show this in a few examples, right? So just for simple demonstrations, so let's go back to the Langue 63. So with these 2 models, right? Here we have, so let's say this is the cross-pollination time windows. This is we starting time at 0 and move to 1.6 unit time, right? Right. We note that usually model A and model B usually they are not necessarily share the same observation space, right? In this case, they do. But in reality, the Meta Office models, the NCAR model doesn't have to share the same model space, but they do share the same observation space, right? So therefore, we can make communications through the shared observation space. So what we do here is, let's say we just take 1 member from each of the forecasts, to make it a simple illustrations. Right. Again, this is X, Y, Z for the Langue 63. Right. So for each of the model forecasts, the trajectories from 0 to the first cross-pollination time window, we can sample it in the observation time to make so-called pseudo observations in the observation space. What this means is actually we can just mix the pseudo observation from model A and the pseudo observation from model B to create a sequence of pseudo observation. What this is saying is that, firstly, mixing, I didn't mean it's averaging. So we see from C's talk, he actually averaged the model output. So normally, I personally would not recommend this. For example, in this case, you can see one model goes up and the other model goes down. If you average them, it's become not physical. Or you can think about if one binary model tells you there's a hurricane and the other model says it's going to be sunshine. If you average them, I'm not quite sure what exactly means. Right. So basically, what I would say is I would rather say using the mix. For example, if I look at the historical data, we maybe say model A is very good in forecasting X and Y, model B is very forecasting Z. So I would just take model A in X and Y variables and take model B from Z variables. In that case, so I could use their forecast trajectory to generate the pseudo observations, then combine them in this is 3 dimensional. So basically X and Y I take model B and Z I take model A. But remember, because I mix them up, so they're not going to be trajectory for any of those models. So that's why I call them pseudo observations, because I could combine them in the observation space. In this case, so the observation space and the model space are exactly the same. Right. Okay, so once we have them, now we have these pseudo observations, we actually can apply a data simulation to the pseudo observation using model A and model B respectively. Right. So the thing is, it could be the case that model A and model B have completely different data simulation scheme. I'm sure that Matt Office has his own data simulation scheme and NCAR has his own data simulation. But that's okay. But they can apply their own data simulation scheme onto these pseudo observations. They have combined in the observation space, right? And then they will generate. Then they will generate data simulation result, but in the future time, right? For this cross-pollination time. And this dashed line are the data simulation result from model A and model B applied onto the pseudo observation we saw before. Right. Right. This is why I call them. This is assimilating the future to explore the richness of the multi-model dynamics. So we're really exploring the multi-model dynamics instead of we just combine them in the end. Right. So similarly, if we apply for the multi-model ensemble, in this case, we will be able to generate from each of the model data simulation, we'll be able to generate these model trajectories in the cross-pollination windows. Once we have this data simulation result, we actually can iterate the ensemble model state at the end of the cross-pollination time, which is here, and run them forward using their own models, because the data simulation result will be able to initialize each individual models respectively, right? So if we do that forward, we initialize the model A using their data simulation result and run it forward. We have another forecast trajectories, and similarly for all the models, right? So this will be the first part of the cross-pollinate time, and this will be the second cross-pollinate time. We can do this again until whatever time you're interested. So basically, if you say we are interested in making a weather forecast for 5 days, we can do this for every 1 day, we can do a cross-pollinations. And every 1 day means that during that time, we actually provide communication between those models at every cross-pollination windows, right? Okay. Right, so we basically can just do this repeatedly. Okay, now let's see how we apply to the Lawrence 96 experiment. So we will set up the system to be the Lawrence 96 model, just one layer, right? So this will be the thing is I adjusted the parameter a little bit. So for the true systems, we will say that the f parameter is equal to 8 in the first quarter of the variables, and 12 at the second quarter, 14 at the third quarter, and 10 in the fifth quarters. And the observation is generated by adding IID Gaussian noise. Right? And we have 4 models. So these are the 4 systems. These are the true system we generate observations. And we pretend we don't know the true system. Where the 4 models just have all the f. They have their own f fixed, but they only write at one particular quarters. So model A is f equal to 8 at all the times. And model 2f equal to 12, and so on and so on. Right. So here is a simple graphic. Right. So this is basically the true system. We can see in this quarter the f is 10 and this is 8. Right. And for each of the models, you see that the f is always fixed, but they are only right at particular quarters. Right. Okay. So how do we interpret the ensemble? So what I would like to do is interpret ensembles into PDFs. So I like the Johan and Smith used to, they published a paper about from ensembles to PDFs. So what we do is we do a kernel dressing. We just put a Gaussian distribution on each of the ensemble members. So here we have a bunch of ensemble members, which is blue bars. And we put the ensemble members, we put a Gaussian kernel on each of them. And eventually, we will generate a PDF, which is not a Gaussian distribution, right? And to evaluate them, we would like to use the probability skew scores. So if you're interested, so there are a whole literature about using proper skew scores to evaluate the probability forecast. I do want to emphasize that using root mean square error, sometimes it goes to it may mislead your result, right? Because especially for nonlinear systems, you don't have a Gaussian distribution, right? So anyway, so if we're looking at the forecast result, so here is a graph of we have 4 models. The y-axis is the ignorance. We use minus p. The proper skew score called minus log p is just ignorance relative to climatology. Climatology is the historical observations, right? So the smaller, the better. So we expect to see the model 1 is doing very well in the first quarter. So x-axis is just locations for the 40 variables, right? And the model 2 is very good in the second quarter, and 3 and the third. This is what we expected because model A, the parameter was correct in the first quarter, and model 2 is the f is correct in the second quarter. Right? And here is the forecasted lead time the first cross pollination time, and the purple the black line is the pure multi-model. So what we do is we just pick which model does best and use their forecast at the particular variables, which means this black line is exactly this one, right? The smallest ignorance, which we pick the variables from each individual models. And the blue line is the CP2 result. But this is only at the first cross-pollination time. Looking at this, actually, we see it doesn't seem that the method improved much, the forecast, right? That sounds a bit odd. We just introduced the method that doesn't improve much. So the problem is, right now, we just made the first communication between the models, right? We used their dynamical information. So we generated states using their own data simulation scheme. But the problem is right now, these are useful informations in those initial conditions. Those information will be useful to making the forecast in the next cross-pollination time. So we expect the information will kick in the next cross-pollination time. Right, so if we go that forward, so this is the second cross-pollination windows. Again, here we just plotted the forecast skill for each of the individual models. Again, we see that model 1, 2, 3, and 4, they are good in each of the quarters. Now this time, we do see that the CPT2 does much better than the pure multi-models. This is because after we made the communication at the first cross-pollination time windows, the information has been feeding into the model initial condition to launch the forecast at the second cross-pollination forecast. Right. Then move on to the third cross-pollination time. And again, we are doing much better than the pure models. And here we actually try to see if we increase the ensemble size, whether the forecast improve or not, whether we can still beat the forecast using pure models. So the orange line was using 36 ensemble members. The original models, they were just 9 members for each of the models. Right? So if we use more ensemble members, it does improve a bit of skills, but the CPT2 uses just 9 members, they're still doing better than all of this. Okay. So in summary, I would say we use the multi-model cross-pollination time for the multi-model ensemble schemes. So it basically explores these dynamical informations, especially in the future. Right? We have demonstrated this in the Launch 96 case, and the most thing I want to emphasize is we used to use data simulation for design for improved state estimation for the past to the current time, but now we are using this data synchronization scheme to improve the future forecast. Right? And the other thing is I'm not saying we have to use any specific data simulation scheme. You can use any of them. This is a tool to provide opportunity to let the model communicate with each other. Thank you. Questions?
Questions? Thank you very much. So, do I understand correctly that you are only picking the model that is the best, isn't it?
In this case,
yeah.
Yes.
And I was running in your benchmark, your truth is actually always choosing in one of the locations there is always one of the models that is perfect.
Yes.
Or you one of your imperfect. Did you try a benchmark where the truth is more like not choosing a perfect model? So out of this.
So it would be nice to find a regime that there's no way to mixing the model in order to get.
Yeah, because that's when I would expect that combining. So not picking one of the members, but combining them, mixing them in a different way. I don't mean the averaging is good. I don't mean the averaging is good, but for us it was a way that we know that none of the models are perfect, and the truth is different than any of them. So we need to find something in between, a way that means. But yeah, okay, thank you.
Anybody want to say something?
No, what's the question?
I wasn't.
You want to complete on this question?
I'm not sure I understood the question. I thought it was that we average things first and then find something, which is exactly what we do not want to do. Because it's bad.
The question was pretty much about whether, because the experimental setup that you had include the truth among the possible models in a way, because one of the set parameter, one of the parameter was the same, or at least in part of the domain. That was the point, right? So that's,
No, it doesn't.
ah, okay. I think it does.
No, it doesn't.
Let me say this. This question might sound like a criticism, but the same concern actually applies to something that I'm working on. So I'm actually quite pleased to see both you and the previous speaker talking about using data assimilation to build this multi-model that can then forecast. What I worry about is sort of scaling up to like an actual sort of weather forecast. This seems to introduce a lot of overhead into the you know, the forecast or just additional processing time. So I was just wondering if you could comment about how this would scale to weather size models.
Well, are you saying it's a computation too costly, or it's a?
That's what I'm worried about.
Well, the thing is, for each of the models, all they need to do is provide their forecast and projecting onto the observation space, which they already can, right? And which they already provided, right? And the communication will be at a particular cross-pollination time. They do another data simulation, and they use their own data simulation scheme. So it should not provide too much of the computation.
Well, what I'm concerned is suppose I want to make a 2-week or a 3-week forecast.
Well, that's a
And
good question.
the operational weather centers now, they don't have to run a data simulation every 6 hours to do that
Yeah, right.
forecast. So that's just what I'm wondering. How simple a data simulation can you get away with? I know the previous talk was nudging.
Yeah.
So-
So what really the model has skills, whether it has skills after 4 weeks or 5 weeks. So if the model itself, the current weather model doesn't have that much skills after that much time, right? So if the model doesn't have much of that skill, that means that the target of interest, the possible improvement from the model, maybe it was just 2 weeks, right? So the cross-pollinating time could be like 2 days or 4 days. So every 2 days and every 4 days you do a data simulation. So that should be cost manageable.
Also, yes, I have a final question as well, just to be sure. What do you call the pseudo observation that is actually there is not observation there? This is
because they are generated by the model.
Yeah, but I mean,
it's not really observation. We didn't observe.
Sure, but you used observation before in order to select
Only
how to combine.
Only from the past. Only from the past.
Okay, if there are not more questions, let's thank Hailiang again.
Thank you.